Okay, let's go through our review, part 1 for chapter 15. Let's dive right in. First of all, number 2 asks, which is greater, an increase in temperature of 1 degree Celsius or one of 1 degree Fahrenheit? Well, when you consider the Celsius scale compared to the Fahrenheit scale, we know that water freezes, let's get a pen here. Water freezes at 32 Fahrenheit or 0 Celsius. And please, I trust that you have a clear concept of the fact that the numbers may be different, but they represent the same thing, the same temperature. So water freezes at 32 Fahrenheit, or known as 0 Celsius. And water boils at 212 Fahrenheit, otherwise known as 100 Celsius. So from here to here we have 100 degrees Celsius. But from here to here we have 180 degrees Fahrenheit from 32 to 212. So what's that tell you? It tells you that the Fahrenheit degrees must be smaller because there are more of them packed into this space here on the thermometer. So a degree Fahrenheit is smaller than a degree Celsius. What's that mean for number 2 then? Which is greater? An increase in temperature of 1 degree Celsius or 1 of 1 degree Fahrenheit? 1 degree Celsius is the larger increase. Celsius degrees are bigger than, they're almost twice as big as Fahrenheit degrees. Which, by the way, makes Fahrenheit degrees more accurate. If you're going to be rounding your temperatures to the nearest integer, talking about the difference between 73 degrees or 74 degrees is a smaller difference than talking about the difference between, say, 22 degrees Celsius and 23 degrees Celsius. That's a bigger difference. So the Fahrenheit degrees are actually a little more accurate. Number 3, why wouldn't you expect all the molecules in a gas to have the same speed? Well, because what is a gas? A gas is molecules flying around and they're bebopping into each other and bam, bam, and a fast one hits a slow one and makes it move faster and that makes this one move slower, and they're always banging into each other all over the place, and so of course you would expect them all to have different speeds. So what is temperature then? Temperature is a way we have of measuring their average kinetic energy, their average speed. Not their absolute speed, because every molecule has a different speed. So we're looking at the average when we're talking about temperature. Number 4, why can't you establish whether you've got a fever or not by touching your own forehead? Well, because our skin makes a lousy thermometer. Our skin can detect changes in temperature. My skin can detect when energy goes out of my hand into something else, like if I touch an ice cube and the warmth of my hand goes into the ice cube. Or my hand can sense when heat goes into my hand, like if I touch the warm burner on the stove and the heat from that burner goes into my hand. I sense those changes. I sense the movement of the energy. I sense the heat exchange. But I don't sense absolute temperature. If I have a fever, maybe my forehead is a little bit on the warm side, maybe it's at 101 Fahrenheit. Well, my hand is going to probably be at 101 also. So if I touch my own forehead, is there a difference? No. My hand is warm, my head is warm. They're both high temperature, but they're both at the same temperature, so there's no flow of energy, and so my skin doesn't detect any difference. On the other hand, just thinking out loud here, if I have been making snowballs for the last hour, and my hand is super cold, and then I touch my face with my cold hand, like, whoa, that hand is cold. On the other hand, if I have been running my hand in hot water, and I touch the same face at the same temperature, then my hand is going to feel warm, because the energy is going from my hand to my face. That's kind of, I guess, a silly, obvious example, but hopefully it helps a little bit. We move on to number 5. a hot cup of coffee or an iceberg, which has the greater amount of internal energy? All right, here I have my attempt to depict an iceberg. And here we have on a table up on the solid ground a cup of hot coffee. Well, this cup of hot coffee has internal energy, enough internal energy to raise its temperature to the point where it is quite hot, but it's concentrated in a small package. There's energy in the iceberg also. The only way to have no energy would be if that iceberg was at absolute zero. What is that, 273 degrees below 0 Celsius? That's the only way for this to have no energy. The iceberg has energy, but it's more spread out in a larger package. But there's a lot of energy there. It's just more spread out. If you took all of that iceberg's internal energy and compressed it down into the size of a cup of coffee, it would be a lot hotter than that hot coffee. Or, on the other hand, if I took the internal energy in this cup of coffee and poured it into the iceberg and let it spread out over the entire iceberg, the iceberg would not be very much impressed. That's a tiny bit of energy. Even though the temperature is high, because it's a small package, that's a tiny bit of energy compared to that iceberg. So yeah, the iceberg has more internal energy. It's just really spread out, resulting in a low temperature. This has very little internal energy, but it's in a tight little tiny package, which is causing the temperature to be very high. So this has less internal energy. Because of its pure size, this has more internal energy. Moving on to number 6. What if you had a thermometer that was made of a kind of glass that happens to expand at the same speed, the same rate as the liquid inside? Well, if the liquid inside and the, say, glass around it were both to expand at the same rate, as the liquid expands, so does the glass expand, what would happen? Nothing. The level would not go up or down. It would just stay at the same place. You may recall that's how a thermometer works. A thermometer works because the liquid inside expands faster than the glass. As the liquid inside expands, it's forced up that thin little tube. As the glass expands more slowly, the liquid is forced up the tube, indicating your temperature. But if they expanded at the same rate, nothing would happen. By the way, did you realize how tiny that tube is? You look at a glass thermometer, and you'll notice that a glass thermometer is kind of triangular shaped. It's shaped like a triangle. That's actually a lens, because the little tube of liquid is a tiny tube down the center, and that glass is shaped so that it makes a magnifying glass that actually magnifies the image of that tiny little tube so you can see it. If that were a round thermometer, you would have a really rough time seeing that thin little tube of liquid in the center, because you could see it, but it would be hard because it's very thin. That's why, have you ever noticed, if you tilt a thermometer different ways, the mercury or the alcohol, the red liquid inside, will disappear or come back in view? You have to get it just right to be able to see it, because you've got to get the angle of that magnifying glass just right to magnify that tiny little tube inside. That really has nothing to do with number 6, but I think it's kind of interesting. Number 8. On which temperature scale does the average kinetic energy of molecules double when the temperature doubles? All right. On the Celsius scale, on the right side here, absolute zero is negative 273. 273 degrees Celsius below zero is absolute. What is absolute zero? Absolute zero is where there is no more energy to take out. the molecules stop moving. There's no more kinetic energy. It can't go in. That's why it's called absolute zero, because it can't go any lower, because there is no more energy to pull out of it. It's out of energy. It's empty. That's negative 273 Celsius, absolute zero. Well, if we come all the way up here to 10 degrees Celsius, that's a difference of 283. Then at 10 degrees Celsius, water is liquid, everything's hunky-dory here. If I then take that 10 degrees and double it to 20 degrees, 10 degrees Celsius up a tiny bit to just 20. Have I doubled the amount of internal energy? Not even close. No way going from here to here, from 10 to 20, no way am I doubling the internal energy. That's why it was suggested by someone a long time ago, Mr. Kelvin, I believe, that scientists might make better use of the Kelvin scale. Because a Celsius scale doesn't have any real meaning in itself. If you double the Celsius temperature, you are not doubling the internal energy. However, on the Kelvin scale, where absolute zero is zero, if you're at 283 Kelvin or 10 Celsius, what happens when you double the Kelvin number from 283 to 566? Are you then doubling the internal energy? Yes, you are. The Kelvin scale has some real meaning because it starts with zero energy. Unlike the Celsius scale, that does not start. Where is zero? Zero might be here. Zero is not at zero energy. What does zero mean? Doesn't mean much of anything. Just an arbitrary spot on the thermometer. But here, zero means something. Therefore, 283 compared to 566 means something. This really is twice the energy. Okay, I think I might have run that into the ground. Hopefully that's clear now, if it wasn't before. Number 9. Why is there a minimum temperature but no maximum temperature? There's a limit to how cold something can get. Why is that? Well, because once you hit absolute zero, that's it, you're done. There's no such thing as negative 10 degrees Kelvin. That doesn't exist. It's silly. Because 0 Kelvin again means all the energy is gone. There's nothing left to take out. You can't go any lower than 0 Kelvin. So there's a rock bottom temperature. But, theoretically, there's no limit to how much energy you can put into something. So there's no maximum temperature, but there is a, bam, right there, 0, a minimum temperature. But no maximum. There are some things in this universe that are very, very hot indeed, like millions of degrees. No upper limit. Number 10. You drop a hot rock into a pail of water. Got a pail of water here. We drop a rock into it. Splash. Here's my rock. A little bit of splashing water here. Okay, splash. Okay, I got a rock in it's a hot rock. Putting that hot rock into the cold water, the energy, the internal energy in the rock is going to go into the water. Energy always flows from an area of high temperature into an area of low temperature. So the heat flows this way, which causes the rock to get cooler, while the water gets warmer. When does that stop? Well, once the rock is at the same temperature as the water, then it all stops. Everybody's happy. There's no more heat transfer. It reaches a point of equilibrium. So the water temperature will rise, the rock temperature will go down until the two are equal. They will come to meet each other. Now the question here though is, in number 10, what if I take that same hot rock and throw it into the Atlantic Ocean? does the same thing happen? Well, believe it or not, here's the ocean, here's my hot rock. Yes, the same thing does happen. The rock will cool down, giving off its heat energy into the surrounding water, which will cause the Atlantic Ocean to rise in temperature a ridiculously minuscule amount. The word we made up for that a long time ago, for an old friend of mine, that would be Danny Smith. Oh, by the way, Smiths, if you're watching this video, yes, I still do give you honor. Danny Smith came up with the word micro-minuscule. Yes, the Atlantic Ocean's temperature is going to go up a micro-minuscule amount, while the rock's temperature goes way down. The rock gives up all of its energy, its internal energy. The rock's temperature drops like a rock, while the ocean, that energy, gets spread out through the entire ocean, kind of like the iceberg question, causing very, very, very ridiculously little change to the ocean temperature. But it's real. I mean, it starts out changing the temperature right around the rock pretty significantly, but then that extra heat dissipates out slowly but surely into the entire ocean until it is practically nothing. Number 11. This is kind of interesting. You've got all this water at the top of Niagara Falls, and it flows down, 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 down to the bottom, and I don't know much about the geography, so I can't give you the names of any places. But the water is flowing down here, it goes splish splash. If you ever go there and listen carefully, you hear splish splash, splish splash. It goes splish splash down here. And the question is, would you expect the temperature of the water at the bottom of the falls to be higher than the temperature of the water at the top of the falls? Well, Mr. Joule, the guy after whom jewels are named, was wondering the same thing and actually did an experiment. He thought, well, because the water up here has something from a long past chapter, it has something called potential energy because of its elevation. By the way, where did it get that potential energy? It got it from water evaporating due to the heat of the sun and going to the clouds and then falling down into the rivers and ends up here with potential energy given to it by the sun. But as it falls, Earth's gravity pulls it down. Earth's gravity causes it to lose potential energy and gain what? Gain kinetic energy as it speeds up, thanks to gravity. So now it has all this new potential energy, but when it hits the bottom down here, it goes splish splash and swirls all around, and all of that kinetic energy then turns into, through friction down at the bottom of the falls, that kinetic energy gets slowed down and is changed into heat energy, internal energy. So one would expect the temperature down here to be a little bit higher because the potential energy here is changed into splish splash thermal energy down there. Well, he ran his experiment. He measured the water temperature up here and measured the water temperature down there and found out that just the opposite was true. Oh no, what's wrong? Physics is broken. You mean the potential energy changed into kinetic energy, changed into thermal energy down here, but the temperature down here was lower? Yes. Why? So simple. Because as the water flowed down here, it was passing through the air, and as it passed through the air, guess what it was doing? It was giving up its heat energy to the surrounding air. Evaporation. Some of the water evaporates as it falls down. And as we're going to see in the next chapter, evaporation releases energy. Evaporation takes energy with it. So the water was actually getting colder as it fell because of evaporation, the heat energy of this falling water going into the surrounding air. The smaller the droplets of water, the more surface area they have, the more easily they can give off their energy to the surrounding air. So by the time it got down here, it was a good bit colder. even though even though the potential energy was changed into kinetic and changed into thermal energy, it gave off so much energy on the way down that the net result was a lower temperature at the bottom than at the top. Surprised Mr. Joule. I wonder what the whole story is and how long it took him to figure out what's going on. Number is a pretty bright guy. Probably didn't take him long. Number 15, a watermelon. A watermelon will stay cool for a longer time than sandwiches if they're both removed from a cooler on a hot day. Why is that? Because guess what a watermelon is made mostly of? Yeah, there's a reason why it's called a watermelon. It's made mostly of water. And water has... Say it. I don't hear you. Well, of course I can't hear you. Water has high specific heat. Meaning that at a given temperature, well, let's put it this way. It takes more energy being put into it to make its temperature rise a little bit. When that watermelon is taken out and exposed to the hot air is putting its energy into the watermelon, but the watermelon's temperature is rising very slowly because it has a high specific heat. Remember, specific heat can be thought of as thermal inertia. It's an object's resistance to a change in temperature. So the hot air goes into the watermelon, but slowly changes its temperature, while that same hot air goes into the sandwiches and increases their temperature rapidly because they have a lower specific heat. So the sandwich gets warm very quickly, the watermelon stays cool for a long time because water has high specific energy. Cold water will stay cold longer, and hot water will stay hot longer because it's very resistant to changes in temperature. It changes temperature slowly as it gives off or as it absorbs energy. Number 17. Hey, we've discussed this one before. I brought back the old diagram here. We're told here again that Iceland has a relatively nice environment as opposed to, say, Greenland. Even though Iceland and Greenland are, let's get a pen that'll show up here, how about red? Even though Iceland and Greenland are at about the same latitude, Iceland is much more pleasant than Greenland. Why? Because of the Gulf Stream. These warm waters coming from the Gulf of Mexico and other places and swirling around here, getting all warmed up near the equator. And that warm water holds on to its warmth very nicely. Comes all the way up here and actually does hit Iceland, the British Isles, places here, Norway and all that, and even Western Europe, and helps keep all these areas warmer, even though they're much farther north than, say, we are. Why not Greenland? Well, Greenland doesn't happen to be in the path of the Gulf Stream. So the coast of Greenland here stays quite cold, while Iceland stays warm because of the warm water and the high specific heat of water, meaning that that warm water holds on to its warmth very nicely as it flows across the Atlantic. Am I saying it doesn't give up any? No, it gives up some of its warmth. It cools down, but it doesn't cool down nearly as fast as other materials would. And it holds on to its heat well enough that by the time it gets to Iceland, it helps them to have a much nicer atmosphere than Greenland. Moving on, it's all about the high specific heat of water. Number 20. We're told that in the old days, folks would take a hot object, maybe a hot rock. They put a rock in the stove or a rock in the fireplace, and they pull it out, and maybe they wrap it in a cloth so you won't get dirty, and they put it in bed with them to help keep them warm. Well, the problem with that is a rock has relatively low specific heat. which means as it gives off its heat energy to you and warms you, the rock's temperature, again, drops like a rock. That rock's temperature drops fast. Gives off some heat, temperature goes way down. Doesn't take too long before its temperature matches your temperature, and at that point it's not going to give up anything more. It's done. On the other hand, take to bed with you a bottle of water, a hot water bottle. That hot water bottle contains much more energy than the rock did, even though the temperature may be the same. That hot water bottle, the water has high specific heat. Therefore, as it gives off its heat energy to your body, oh, thank you, its temperature doesn't go down nearly as fast as the rock. It still has lots of energy left to give you. It takes a lot longer for the hot water bottle's temperature to get down to the point where it matches your temperature. So it continues to give off warmth to your body for a long time. Paul Hewitt suggests that it might see you all the way through the night. I don't know if it'll do that well, but it'll do a lot better than the rock. And he says on number 21, the desert sand is very hot in the day and very cool at night. Goodness, you don't have to go to the desert to experience that. Go to Ocean City and you can experience that. You walk on the beach at night in bare feet and it's very cool. You walk on that same beach in the middle of the day and it's very hot. It's like, oh man, where are my sandals? What does this tell you about the specific heat of sand? Specific heat must have very low specific heat because it doesn't take much to change its temperature. You put a little bit of sunlight in it and its temperature goes whoo. You take away the sun and its temperature goes whoo. It changes its temperature very easily. It has very low thermal inertia. It's very easy to push its temperature around. Put a little bit of heat in, temperature goes way up. You touch it, it's like, whoa, that's hot. You take the heat away, take the sunlight away, and it gives up its heat to the air, and its temperature drops down. Unlike the ocean itself stays at a pretty much steady temperature all the time, day and night. Because the ocean is going to give up, as it gives up heat to the air, its temperature changes just a little bit. Sun comes out, warms it up, energy goes into the water, it raises the temperature just a little bit. Because it has high specific heat, high thermal inertia, we could call it. I think it helps a lot if you think of specific heat as being, as Paul Hewitt suggests, thermal inertia. Sand changes its temperature very easily, so it doesn't take much to make it get hot, doesn't take much to make it get cold. Water has very high specific heat. It takes a lot of energy to raise its temperature a little bit. Okay, and that ends part 1. So stay tuned for part 2. Chiefs and people, you can simply click the link to the next section and keep on going if you want to, or save it for later. But part 2 is coming, beginning with number 22 next. See you then.